Hello, we are Team Fruse from Quantum Software. My name is Shravika Pindiala.
Hi, I'm Mina Chan.
I'm Grant Sackman.
And I'm Daniel Cho, and for our BWSI final project, we explored the variational quantum classifier.
But before we begin explaining this algorithm, let's first talk about what quantum computing is. Quantum computing is a new and exciting area of computing where principles of quantum mechanics are applied. Quantum computing uses units of data known as qubits or quantum bits. While a normal bit must be either a 1 or a 0, a quantum bit can be in a probabilistic state of both a 0 and a 1. This is called superposition, the first fundamental property. While superposition allows for the creation of these possibilities, interference amplifies the possibilities we want and reduces the possibilities of the state we do not want when we finally measure the qubits. Taking the analogy of a coin, using superposition and interference, the coin is now spinning, but we only know if it's a heads or a tails once the coin stops spinning. This concept is known as measurement, and the last fundamental property is entanglement. This is when we measure a single qubit, and based on the output, we're able to determine the states of the other qubits.
The main advantage of having these properties in quantum computing is parallelism, meaning that whereas in classical computing one step is completed at a time, in quantum computing all steps are happening simultaneously. As a result, quantum computers can perform on multiple qubits at once. Quantum computers use less resources and may perform less operations on tasks. Yet there are some limitations. Due to the modern hardware obstacles of quantum computing, we are limited in the number of functional qubits we can use. Since the current hardware is not sophisticated and reliable, we ultimately chose the variational quantum classifiers as our final project. Our goal with this algorithm is to predict whether a person is at high risk for heart disease from a set of data features. In order to do this, there are 4 stages of implementation. The first stage is pre-processing. In this step, the original data starts as unorganized classical data. We want to analyze the parameters and figure out which ones are important to feed into the algorithm. So we found the 4 most important features, isolated them, and normalized them, changed the range of values. The second stage is a feature map, which converts the modified classical data into quantum data that can be run on a quantum computer. As shown in the image, the goal is to find the correct slope of the plane that classifies the data, separating the red from the blue. In terms of implementation, we want to perform a series of operations on the qubit to encode the data we want.
Next, a variational circuit is applied to the qubits. The variational circuit rotates the state of each qubit and entangles them, which effectively changes the weight of each parameter that will be considered on the final output. In other words, it further changes the probability of either measuring a 0 or a 1 through parameterized arbitrary rotation. Finally, after reading the output, the computer makes slight changes to the parameters of the variational circuit until we reach a minimum value of the cost function, which is what we want. The minimization was handled in 2 different ways: SciPy's minimization algorithm and a naive looping method that we wrote from scratch. Ultimately, the 2 methods yielded the same cost function minimum, which is 0.25. As for resource usage, our algorithm takes, on average, 10 minutes to process through 624 lines of input data for 30 iterations each. This includes rebuilding the circuit for each input and then adjusting the parameters and remeasuring to calculate costs. Our circuit takes 4 nanoseconds to build, and the space complexity in terms of qubits is logarithmic, with respect to the number of features that we have for each dataset. The circuit depth is 5, meaning the largest number of gates a qubit encounters on any given path is 5, which is good because we want to minimize the number of gates we encounter so that we run into less error in the NISQ era quantum computers.
Throughout our process, from finding what we wanted to create to building our final product, our team faced many challenges. All the literature that we read were from academic journals that are filled with high-level jargon and complex math. While some explanations were too high-level, others were too abstract, and didn't provide us with enough information to properly implement our algorithm. Additionally, due to quantum computing being so new as a field, it was very hard to find good documentation and resources. An example of this being, some programming libraries were outdated and no longer supported. Another issue we ran into was dividing our task among group members. Many parts were interlaced and depended on previous members' portions to work. as well as being uniquely complex, it was very hard to help everyone. But through hard work, effective communication, and collaborative teamwork, we were able to successfully implement our algorithm with the results you saw prior. Thank you.